Okay, what we're going to work on today is some basic skills that we need to make sure we know in order to do statics problems. These skills are going to be basically resolving angular forces, resolving distributed loads, and also looking at moments to make sure that we correctly calculate and determine the sign of those moments. First up is resolving angular forces. Now, if you take a look at this triangle, any force that is at an angle like this F here or this G here needs to be resolved into horizontal and vertical forces. This is going to allow easier calculations to do that. Okay? When we do this, when we resolve forces, we're going to use our trig functions. Just to review our trig functions, if we have this angle here, okay, and you can see that this is a horizontal angle because it's adjacent to a horizontal surface instead of a vertical surface. We're just going to use this triangle to make sure that we have the trig functions laid out correctly. We've got the sine is going to be the opposite over the hypotenuse, and remember that's abbreviated SIN. We've got the cosine is the adjacent over the hypotenuse, and that's abbreviated COS. And then we've got the tangent, which is the opposite over the adjacent, and that's going to be abbreviated TAN. Okay, so if we've got this angle up here, we're going to look at both the vertical and the horizontal angles here. This one is vertical, so we'll do that one first. And I'll go ahead and type this over here. So if I'm basically trying to resolve the forces, I'm trying to get this F into Fy and Fx components, okay? So what I want to do is I want to go ahead and say Fx is going to be equal to F, the hypotenuse, times either the sine or the cosine of it. If we take a look at this, the Fx is opposite of the angle. So that means that we are going to use sine of theta. So I'll click theta on my symbol to insert that. Okay, so F sine of theta is my Fx. If I want to go ahead and make my Fy is going to be equal to F, and we'll see that is adjacent to the angle, so that'll be cosine of theta. Okay, so these are my resolved angles for this particular triangle. Okay, now for the second one, these are a little bit different here because the theta, the angle in question, is adjacent to the horizontal. So that'll be a little bit different. My GX is going to be adjacent to the angle. So instead of sine in this case, I'm going to use G cosine theta. Okay, and then for the GY, you take a look at it, the GY is opposite of the angle, so that is going to be the sine theta. Okay, so that should review that. So remember your trig functions for that particular item in statics. Now the second item that we're going to talk about is resolving distributed loads. So a distributed load is a load that has many arrows down, and this one here is an a uniformly distributed load, and this one is a triangular load. So the uniformly distributed load exerts the same amount of force for every meter or every foot along the beam, okay? So what we need to do is we need to basically break this down, this rectangle, into a single arrow, okay? And I've got a little bit of a formula here for you. So this uniformly distributed load, we'll call that force F, and then we'll call the length of the beam L, okay? So what we need to do is we need to resolve this so we can basically find the value of the load. Okay, and the value of the load is simply going to be the area of the rectangle. Okay, so the area of the rectangle is the height, which is going to be F, times the length, which is L. So that is going to be the value of the load, okay? And the location we need to determine as well. For the location, it's going to be located in exactly the center. So the location is going to be located, and I'll say at L/2. It's exactly in the center, okay? Now for the triangular, and I'll go ahead and type up here, we'll say that this is the uniform. And we'll say that this is the, skip a line, this is the triangular. Okay, and for this one, we need to determine the value of the load. And just like we did up here, we found the area of the rectangle, we're going to find the area of the triangle, okay? So this is going to be the length times the height, and here I've got a value for the height, WO, we use capital WO, times length, but it's going to be all of that over 2. So I'm going to go ahead and put my brackets in here, where we know that we have to divide that whole thing by 2. So that's exactly how we find the area of that triangle. The load in this case, you can see there's a diagram, it's 1/3 from the large end of the triangle. So the location is at L/3 from WO. Okay, so that's how we determine that. Now the other type of distribution that we have is a trapezoidal distribution. If we take a look at the trapezoidal distribution, we can actually simplify this. Instead of 1, we'll have to simplify it into 2 loads. So if you can imagine drawing a line across here, you'll see that this is basically going to be divided into a rectangular load and also into a triangular load that's on top of one another. So for the trapezoidal load, we have 2 that we are going to simplify. Okay, the trapezoidal will have F1, which will be the load due to the even distribution or the rectangular. So we'll say that F1 is going to be equal to, and it looks like we have WO1 here. So we'll say WO1 times L. Okay, that is going to be there. And we'll give the distribution at L/2. Okay, now we've also got this second load, F2, which basically represents the triangular portion that's on top. Now we've got to be careful when we determine the area of this triangle here, because we don't want to include the area that we've already accounted for. So this side right here is going to be WO2 minus WO1. That way we only consider this short end of the triangle. So for the top, I've got to say WO2 minus WO1, okay? And I'm going to multiply it by L. And when I do that, I'm going to also have to divide the whole thing by 2 because it is a triangle, okay? Now the location, we can either use the L/2 or the L/3. I'm going to use the L/3. The L/3 from the WO2 end, okay? So that is showing you how to actually simplify these complicated shapes into simplified loads. Now the last thing that we're going to talk about is moments. Now a moment is going to equal a force times a distance, okay? So you can see that what I have here is I've got this beam that's right here, beam AB, and I went ahead and put X's here because we're going to take the moment about A or the moment about B. Now what we need to do is we need to figure out what the value of the moment is, and we also need to figure out the signs. Okay, so what we are going to do, moments about A, we are going to say that we have M times L1. Okay, that is the size of the moment, but we need to look at the direction. We need to use something called the right hand rule. And it's basically you're putting the wrist of your hand at the moment, at the point where you're taking the moment, and you curl your fingers in the direction. So if I'm holding my hand, my wrist here, and I'm curling my fingers in that direction, it's going to give me a positive moment. Another way to think about it, I like to use what's called the clock rule. If I put the center of a clock here, okay, and I think about how angles are counted. If I put the center of the clock here and I'm going in the counterclockwise direction, it is going to be positive. So here, my moment is going to be positive. If you want to put a plus in front of it, that is there, okay? So there's another moment about A, okay, and we're going to use that for the N. If you take a look at the N, and we have another distance of L2 here. Okay, now let's look at the sign for that. If you take a look at the sign for that, the moment about A for N, this is going in the opposite direction. So if we use the clock rule, we put the center of the clock here, it's moving in the clockwise direction, it's going to be negative. So we'll just have to make sure that we specify the sign in front of that, okay? Now, we can also take the moments about B, okay? So we're going to practice that as well. Moment about B for the first one, we'll look at M first, okay? I've got M, and in this case, I need to get the distance of this moment from B. I can't use L1 because that's the distance from A. So what I have to do is I have to take L minus L1, and that'll give me that distance that's left over. Okay, but I've got to look at my clock rule. Okay, if I put my clock here, the center of my clock here, and I'm moving in this direction, that is going to be clockwise. So that means that that moment will be negative. Now the other one, okay, if I take a look at this, okay, and we find that this is the center of the clock, and I've got my N is my distance. Sorry, is my force. My distance is going to be L minus L2, okay? Because I can't use this one. This is from A. I have to use the distance from B. And if I take a look at this, I put my center of my clock here, and I'm moving in the counterclockwise direction. So that means that'll be positive, okay? So these are the different moments that exist, okay? And what I'll do is I'll label this as a 1, I'll label this as a 2, I'll label this as a 1, and I'll label this as a 2. Okay, so hopefully that helps you understand a little bit better. And what I'll also do down here is we're going to type counterclockwise is always going to be positive, and clockwise is always going to be negative. So you just have to remember the clock rule. Put the center of the clock on the point in question, and then use this here. Okay, good luck.